Good afternoon and welcome to the joint Astronomical Colloquium here in Heidelberg. It is a great pleasure to welcome Ignas Snellen from the Sterrenwacht Leiden to talk to us about exoplanets and the search for extraterrestrial life. I think that is a topic that is very dear to all of us and very interesting, not just to astronomy and astrophysics, but to science and the general public. So a few words on the speaker. Ignas did study in Leiden. From that he went to Cambridge, UK. From that he took a lecture position in Edinburgh, and in 2004 he moved back to take a faculty position at Leiden University at the Sterrenwacht, and since then he's there. He's very well known for his work on exoplanetary science. He got very distinguished grants and fellowships. Let me just mention two. One is the VD of the of the Dutch Science Foundation. Veni Vidi Vici, so this is the highest of these grants they give out. And 2 years ago, 1.5 years ago, in 2016, he got an advanced ESC grant. So, welcome to you, and welcome to the speaker.
Thank you, Ralph. Can you all hear me? Yes, the microphone on, or it's green, but
okay, it's green. How does it work in the back?
Yeah. Okay. It's very nice to be here. I've visited the city many times, but normally I go up the hill, so it's nice to be here in the actual city. So when you work on extrasolar planets for a while, you start to forget that only 25 years ago or so, the only planets that we knew were in our own solar system. And in 1992, the first planet in very extreme circumstances were actually found. In 1995, the first hot Jupiter was found. And it's really the kind of a start of an exoplanet revolution. The first transit, now already 17-18 years ago, the first measurements of an atmosphere, planet thermal emission, 2008, the first direct image. Now already again a while ago we reached the point that we had 1,000 extrasolar planets, and only last year I think we found first evidence for a real exo-Earth. Now this revolution is not because we are getting smarter, at least most of this is not because we are getting smarter, but that's because the instruments that we are using are getting better. For example, the actual the precision at which we can do Doppler wobble measurements has actually improved by about a factor of 1,000 in a bit more than 30 years. And because of this improvement of instrumentation, we can actually look into the future, because we know there are two great observatories are coming online. The James Webb, which will hopefully be launched in about 1.5 years, and we have the EELT. And now, in the second half of my talk, I will show you how I think that in the next decade, these great instruments will actually teach us about the atmospheres of Neptune, the atmospheres of Earth, and then hopefully also we can start to try to observe biomarkers and get the first evidence for life outside the solar system, if this of course exists. But maybe first we should just briefly mention, okay, what are the main scientific questions in this field? It's all about placing the Earth and our solar system in the context of the universe. Now we want to know, how do planets form, what ranges of architectures of planetary systems do actually exist, and how does the solar system fit in? And yeah, the actual question that I really like is, and the main reason why I'm in this field is, do other life-bearing planets exist? And it's very nice because maybe within my lifetime, hopefully another 30, 40 years or so, we will get an answer to this actual question. Now, when we talk about planets, it's maybe good to first look at the planets in our own solar system, because there are already very important lessons that we can learn from that. And it shows that planets are very complex and show a great diversity. For example, we have the gas giants. These are molecular hydrogen dominated. Much for clouds, strong zonal flows. We have these storms. We have the great red spot here, the size of the Earth, which has been raging for hundreds of years. And then when we move on to the rocky planets, there we see that this diversity is even larger. We have sort of 4 Earth-like objects within the solar system: Venus, Earth, Mars, and Titan. We see that Venus is although it has the same mass and the same radius as the Earth, the atmosphere looks actually very different. Whoa. Doesn't like the movie I'm playing, apparently. There we go. Now, Venus has a super-rotating carbon dioxide-based atmosphere with a strong cloud deck. I should skip this. It doesn't like this view graph, clearly. I'll show it in this way, and then I'll move it on. Of course, we have the Earth, which is molecular nitrogen-based. That's mainly in the optical clear atmosphere. It has a significant part of oxygen. We have Mars, which is again a carbon dioxide atmosphere. It's very thin. For example, it has trace amounts of methane that we do not know why it is actually there. And then we have Titan, which is again a nitrogen-based atmosphere. So what we would really want to understand, okay, what is the link between all these different planets? And the way I like to see that is in the context of one of my great heroes, Charles Darwin. It's like trying to actually get what the tree of life is when you have only 3 animals. Right? If you only have an owl, you have a monkey, and you have an actual scorpion, how can you ever find out, what the history and the evolution of all these species is? So what did Darwin do? Of course, he went onto this epic voyage. Now along the coast of all these great islands. Now to actually find out, gathering evidence for his great theory. And I like to see the exoplanet research in a similar way. We are on this great voyage. It will be very difficult to get information of all these distant planets, but that will be the only way to also learn about the planets in our own solar system. So we have had now 25 years of exoplanet studies. So just in one slide, what have we learned so far? Well, basically that the actual diversity is even larger than we see in our solar system alone. There are these classes of planets that we didn't know exactly existed. For example, the hot Jupiters, gas giant planets at very short orbits of only a few days. It's clear that they cannot have formed at such a short orbital distance, so they must have formed much further away and migrated inwards. This is already, again, I think it's a very nice example how exoplanet studies are already teaching us something about the solar system, because these processes of migration, they seem to be important also for the history of our own solar system. Then we have a whole new class of planets here. Now, in a solar system, there's a clear gap between the rocky planets and between the gas giants. We see clearly there is actually a large population of planets. It's often not clear whether you should call them super Earths or mini Neptunes. And then we have these, again, massive gas giants at very large orbital distance. They can be up to 100 AU or even further away. And also for those planets, it's not clear how they have formed, and maybe they have formed actually much closer inwards. If you look at the solar type stars, then we see that about 1 in 10 stars host Jupiter mass planets. About 1 in 5 stars host a Neptune mass, and most stars have Earth mass planets. So I'm not saying that these are Earth-like planets, but these are planets with the mass of the Earth in any possible orbit. Now we really want to understand for a whole wide range of planets, a function of mass, function of distance to the host star, maybe also for different characteristics of the host star, what all these possible atmospheric processes are and what the evolutionary histories of these planets are. Because I think this is a key ingredient to at some point really unambiguously identify extraterrestrial life. Of course, and I'll show you later that the way we think to get the first evidence for biological activity on other planets is to look for oxygen, because we know that the oxygen in the Earth's atmosphere is only here because of the biological activity. But if you see that on a different planet, you have to first make absolutely sure that this molecular oxygen is not caused by some kind of other non-biological process. Okay, the nice thing is that we had a great year. This will be a very difficult task. I hope that in the next 10-15 years we will see molecular oxygen. I'll show you later how I think we will be able to actually do this. But what is very nice is that this has been a great year. There has been 2 or 3 very important discoveries. The first is Proxima B, radial velocity planet around our nearest neighbor, found to be about in an 11.2 day orbit, about 1.3 times the mass of the Earth, and it receives somewhat less radiations from its host star than the Earth does from the sun, but it's well possible that liquid water is actually present on this surface, and therefore, this could be a place where life exists. What is nice is that the way they observe this with the Harps spectrograph, and they keep on doing this, and there's now also evidence for a second planet in a much longer orbit, about 100 days or so, Proxima C, and it just shows you that these rocky planets, Earth mass planets, are very common. We can, at this point, we can really only see them around these very low mass objects, but it's clear already around low mass stars that they are very common. There's also another recent measurement that came out a couple of weeks ago. That's another very nearby M dwarf, Ross 128. Also has an Earth mass planet about the same mass as Proxima B in a slightly shorter orbit, and therefore a little bit hotter. But it seems to be that everywhere we look and where we would be able to find Earth mass planets, people actually see them. Then there is another great discovery, that is the TRAPPIST-1 system. This is these are found with transit observation. This is a very small star. About the smallest star that you could actually get is about 80 Jupiter masses. And as found, there are actually 7 transiting planet. They're all about the size of the Earth because of the interaction, the gravitational interaction between the exoplanets. Gives us very small transit timing variations. From that, they can also estimate masses. They're all about the mass of the Earth. So we have really a system of 7 Earth mass planets, and yes, several of them are irradiated in such way that there could well be liquid water on their surface. So this is the incident flux. One is the incident flux of the Earth. Here is the radius of the planet, and you see there are several that could well have liquid water on their surfaces. So the remainder of my talk is going to be how could we further study such a system like the TRAPPIST-1 or the Proxima B. And that is all about characterizing the atmosphere. And then you have to realize, although thousands of planets have been found so far, that almost all of them have been found without identifying a single photon from the planet itself. Right. And if you want to do an atmospheric observations, you can no longer do this. You really have to start identifying photons which are coming from the planet, and then you have to think, okay, and how am I going to do that? So there's basically 2 families of methods to do that. There's a time differential method that we basically uses transits or actual eclipses, meaning that as function of time we see the planet star system change, and therefore by looking at these these changes, you can extract the actual planet signal. I'll show you some example of that in a moment. And you have an angular differential method, and that's basically direct imaging, trying to angularly or spatially separate the star from the planet in the sky. Now, what you do when you do transit measurements is basically this. Is when you have a planet orbiting a star and it moves in front of the star, the exoplanet blocks a little bit of starlight, but also a little bit of starlight is filtering through the atmosphere, and basically and when it happens, absorption happens, and that alters the actual spectrum, and by measuring that you can identify what kind of atomic or molecular species are in the atmosphere. Another way is that you look at eclipses, and that means that when the planet moves behind the star, there are periods that you don't see the planet, so therefore you can actually derive the light or the emission that you are missing is coming from the exoplanet, and therefore you can derive what the actual, for example, thermal emission or the reflected light from a planet is. Now, how does this work in practice? When you have a transmission spectrum, is basically you have the planet, and the planet is blocking a fraction of the light. And but when you then look at certain wavelengths, there is extra absorption because of the atmosphere, the ring of the atmosphere around the planet. Here, the ring is shown, the atmosphere is shown very, very large. So that means that the effective radius, so the actual depth of the actual transit, changes as function of wavelength. And by measuring that very accurately, you can show that here. You can see that here. This is absorption. So this is basically the transit depth or the effective radius of the planet as function of wavelength. Here going from 1.1 to 1.7 micron. Is that you see the blue points on the data? Is that here around 1.3 micron? Certainly the planet radius appears larger, and then it goes back down again. And this is because of extra absorption of water in the water vapor in the atmosphere of such a planet. Now, this is done with the with the HST. Here's another very nice measurement with the HST. This is the UV optical, and there you see that when you go further to the actual blue, that the radius, the effective radius of the planet seems larger, and that is thought to be due to Rayleigh scattering. Most of these type of observations are done with the HST and Spitzer, and on these very hot Jupiters, because those are the ones for which the scale height of the atmosphere is the largest, and you are looking for signals which are about 10 to the minus 3 to the minus 4. So there has been a very nice Nature paper last year showing a sample of these hot Jupiters, measuring both the Rayleigh scattering slope and the water feature. These are about 10 or 12 or so of these hot Jupiters, and what they very nicely see, I think, is that the stronger this Rayleigh scattering slope, the higher this Rayleigh scattering slope, the less strong the water signal is. And that you can actually see that here. This is the strength of the Rayleigh scattering feature, and this is the strength of the water feature. What people think this is actually because of hazes. The more hazes you have, the more particles you have in your atmosphere, the less clear you can see the actual water feature because of these other absorption processes. Now, people have tried to actually push this further, to go to super-Earth regimes. This is, first of all, much more difficult because the planets are smaller. Also, for most planets, the extra temperatures are lower, so the scale heights of the atmosphere are lower. But there are probably other problems. So this is the famous super-Earth, GJ1214. And what people see is that this is again with the HEC that this transit spectrum is very flat, and that means that there must these features that people expect there to be are some way muted, and that could well be because of actual clouds. So when you go to cooler objects, these kind of transit measurements become even more difficult because you have extra, because of cloud features that make these signals smaller. Right, let me see. Let me skip this one because I don't have time. The actual transit method has a really great future in front of us with the launch of the James Webb. We really hope that this will make observations order of magnitude better. Not only one of the main reasons is that the actual wavelength range will be so much larger. So there will be some very exciting work will be done with this in the near future. I want to concentrate more on from now what we do in our group. What we focus on is how can we use these time differential method and these angular differential methods best from the ground. And what we have learned, what is a very powerful way of doing it, is to combine these classes of method with spectral information. And the way that actually works is that you also expect the spectrum of the star to be significantly different from the spectrum of the exoplanet, and you can use that information to further separate out light which is coming from the planet and light which is coming from the actual star. And you can use that both in a time differential method, so during transit and actual eclipses, and you can use that with direct imaging. And I'll show you now some examples of what we actually do. So it's important that for this method we use a spectrograph with a very high spectral resolution of about 100,000, and that means that when we probe an actual molecular band, we don't probe the band as such, but we probe the individual lines within the molecular band. It can be tens or maybe even hundreds of lines. And that's important because then we become sensitive to the strong Doppler effects due to the orbital motion of the exoplanets. Right? So the Earth has an orbital motion of about 30 kilometers per second. When we talk about a hot Jupiter, it can be up to 100 or 150 kilometers per second. And it means that during an observation of a few hours, the radial, the component of the orbital velocity can actually change by several tenths of kilometers per second. And therefore, when you would probe absorption lines within your spectrum, planet absorption lines within your spectrum, these planet absorption lines move. And you can use that movement to separate out any light or any spectral features that are coming from the star or from the Earth's atmosphere, which we have to look through. This is an example. This is just a toy model of carbon monoxide at 2.3 micron. And this is orbital phase, so this is time. Here we see the axial transit, and this is the orbital velocity. This is the Doppler effect making the orbital velocity and the wavelength of the planet lines in white change. And in black zijn any absorption lines from the star or from the Earth's atmosphere. So we can use that movement to filter out anything which is not moving and focus on the actual planet light. Now this is an example of that. This is now using the Cryo-S spectrograph on the very large telescope. This is again time, and this is velocity. This is more or less the beginning of the transit. This is the end of the transit. You have to squeeze your eyes maybe a little bit. And this slanted line here is a combination of several tens of CO lines, which are shown in this very simple toy model here. And basically what is nice is this is now a measure of the orbital velocity of the exoplanet. So we know what the velocity of the planet around the star is. We know also, we knew that already from the earlier Doppler measurement, what the velocity of the exostar is. So now we have actually the velocity of both objects, and we can treat this as a binary object and solve for the exomasses without making use of any model except for Newton's law. We also see evidence that you would expect at orbital phase 0 that this goes exactly through zero velocity. But we see evidence, although it's only 2 sigma, so that this is a little bit blue shifted. And we think that is interesting because that may be a real effect, what's happening when this planet moves in front of the star. Basically the hot day side is on the back of the planet, the cold night side is in the front, and we probe this ring of atmosphere around this planet, and you would expect that there to actually be global winds blowing from the hot day side to the cooler night side. So you would expect any gas that you actually observe in this ring to be blue shifted towards us. This is for transit observations. You can also do that for day-side observation, and then you have to realize that here is the actual eclipse, and during the eclipse, there's not really a reason to actually observe a planetary system because you cannot see the actual planet absorption lines. And this also means that you can actually use this method on non-transiting planets. And that's what we did next, because that is the great benefit that we can go for more nearby stars. We have more flux, and we can do this more accurately. So we did this for Tau Botus. This is a magnitude 3.5 star or so. We had 3 nights on the VLT to actually do this. You can see here, this is about the orbital phases that we actually covered. And we did the same analysis as we did for the transit, and we get a similar plot. This is again orbital phase with the 3 nights, and this is now velocity. And you have to really squeeze your eyes. I have the guiding lines here. This is actually the planet signal which is going through this data set. So this planet is really swirling around the star here, starting at plus 80 kilometers per second down to about minus 80 kilometers per second. Now, per spectrum here, it's only at about a 1 sigma level. You can see it a little bit better in this when it's in the planet frame. So what we can do, we can now add up the actual data in the actual time frame. And what is nice is that because this is a non-transiting planet, we don't know what the orientation of the orbit is. And if it was a face-on orbit, you would expect the planet signal to be like this. And if it was really an edge-on system, it would move much faster in velocity. So we can add up this signal assuming different inclinations, and that's what we did here for different inclination. And we can also do it for different system velocities, although we know what the velocity of the star is. And this is this diagram, and there you can see, yes, there's a clear signal. It's about 6 sigma. It's at the system velocity of the star as we knew it to be. And this implies then it is an inclination of about 45 degrees. Now, we did this now for a handful of planets. You have to realize we can basically only do this for the very bright stars. So there are only really a handful of planets we can do that for. This is again for Tau Bovis. This is the mother of all exoplanets, 51 Pegasi B. It actually turns out to be an almost transiting system. It's actually, we see it a little bit above an inclination of 90, but that is due to the uncertainty of the mass of the actual host star. So it has an inclination of above 80 or so, if you include all the errors. And this is of an actual transiting system, the day-side emission. And there we know not only the system velocity, but we also know, okay, it has to have an inclination of 90, so we know that the signal should be actually there, and we see it. And the same signal we see also in water at much longer wavelength in actual L band at 3.2 micron. Now this is going to be a very powerful method. CRIRES has been off the actual telescope for about two years now because it's undergoing an upgrade. The wavelength coverage is going to be about a factor 10 larger, and it's really opening up a whole new parameter space. And hopefully from next year we can start to actually use that. Another very interesting instrument is the Espresso Instrument, and that's basically the harps, but then for the VLT. And we will, it's very interesting for reflected light and for metal oxides. And has been recently, last week, has been a very nice result. That with Subaru, that at a resolution of 160,000, they actually start to see the TiO molecule in the thermal day side of WASP 33. This is actually the actual injected data. And here you see, if you squeeze your eyes a little bit, here you see the actual pattern of what you actually expect. If you then, in the same way as we always do that, integrate over time, then we see the nice signal. The black lines indicate this is where you expect where the actual signal should be. So also this is very nice. For example, with the actual Expresso instrument, we will be able to actually do this for many more instruments. Okay, so it's this is very much photon limited science. We need a lot of telescope time, even for the brightest and the most nearby objects. So that's already implicitly tells you that this is going to be great for the ELT. There are many science cases I don't want to go into because I don't have time. I just want to show you that I think that with the ELT there is a good chance that we will be able to measure molecular oxygen. So this is what I would say is the ultimate science case for for the ELT, what if you now take the exotransit spectrum of the Earth and put the Earth in front of an M5 dwarf? This is what the effective radius of the Earth is in the oxygen A band at 7600 angstroms. See these very nice, spatially separated lines. They go up to about 85 kilometers altitude in the Earth's atmosphere. And then with this knowledge, you can just very simply, okay, what if we have a copy of the Earth and we have a transit in front of an M5 dwarf? What kind of transit spectrum do you expect within the oxygen band? And that's this spectrum. We have a signal, we expect a signal of about 5 times 10 to the minus 5. And what is nice, if you compare that to the carbon monoxide, a model of the carbon monoxide signal that we already observed in tau Bodus B, and then you see that this is actually only a factor 3 larger, the signal, than what you expect for molecular oxygen in an actual transiting Earth. Now, factor 3, you think, okay, that's nice, but the problem is this is a magnitude 3 star, and this will be a much fainter star. This will be a magnitude 10 or a magnitude 11, and therefore you will need a very large telescope, extremely large telescope, to actually do this, to have enough photons. Now you can actually go through these numbers. How many photons do you actually need? You take an M5, you can calculate, okay, what is the probability that it actually transits? At what magnitudes do you then expect such a transiting system to actually be? About magnitude 11. What is the contrast of the lines? 5 times 10 to the minus 5 in this case. You get about a 1 sigma measurement per exotransit. So if you want to have a 5 sigma measurement, you have to add up 25, 30 transits. You'll have a few transits a year to actually observe. So that will be a project of about a decade. In that decade, you would then need 25, 30 nights to actually do such an observation. If you go to larger stars, then you immediately see that this is going to be a problem. For Earth-like stars, indeed, you can get maybe a 1 sigma per exotransit, but because these transits only happen once a year, and during the exotransit it has to be night, and the star has to be actually up. That means you can only observe a transit, one transit in a few years, and that means that your 30 or so transit you will take about 100 years to actually collect, which start to be in the actual realm to be a little bit difficult. The nice thing is that since last year we have real objects now, so we can put in real numbers. For example, the TRAPPIST-1, we can put in, this is an I-band of 14, and we would need, it has a signal to noise of about 0.7 then, and that's because the contrast is actually somewhat better, and that's because the star is even smaller than this M5, and again you would need about 5 to 10 years to actually collect enough transits to actually do this. And maybe in that case it may actually be better to go to a different band. There is also a very nice oxygen band in J band. It's a lot brighter, and maybe we can actually cut this time. But it really means that when we have the right instruments on the ELT, and I'm talking about the high-res instrument, we will be able to actually do this oxygen measurement. Okay, that were examples of doing these time differential measurements, including high dispersion spectral observations. Now we want to show the same method, but then including direct imaging. And just to start from a very different viewpoint, actually this idea has been around already for about 15 years ago. When I was writing a paper about this, I didn't know about this earlier work, or only found out much later, even after it went to press. Schneider emailed me, but we did this already in 2007, I could email him back that I didn't know that, but that they didn't actually reference them either. So we all didn't actually know, and that's because everybody is using different names for this game. So what is the XL there? This is a nice example of a high contrast image. We have the star and the residual of starlight with speckles here. We have a planet. And yeah, we want to observe as faint as possible planet as close as possible to the actual star. And what is the problem now is we see these blobs here. How do we know what is a planet and what is a planet and what is just a residual speckle? Now, what is if you have spectral information, you can actually do this because these speckles will have the spectrum of the star, while the planet blob will have the spectrum of the planet, which is in most cases very different. The planet spectrum is very different from that of the host star. Just an example of how well this works. We did recently an experiment on archival symphony data. This is not at a resolution of 100,000. It's only at a resolution of 4,000. But yeah, that's the only that are the only integral field units available now. It means for every pixel we have an actual spectrum. But if you look at the white light, yeah, this whole image is completely dominated by light from the actual star, and at the position of the planet, it's somewhere here. That's actually still, you only see starlight at about a level which is 250 times lower than the actual starlight in the center. Now, the nice thing is that although there's starlight everywhere, we know the spectrum of the star really well because it's everywhere the same in the whole image. So the next step is that we actually remove as well as possible the starlight from each pixel, and then on the residuals we are searching for the typical spectrum that we expect for, in this case, beta Pictoris B. And this is a bit of magic. This is what you get then. This is when you cross-correlate with a model of about 1700K of BT saddle, and suddenly you see this exoplanet very, very clearly. And that's because of the CO and water lines, which are only present in the exoplanet spectrum and which are not present in any of the other pixels present. Instead of a raw contrast of 250, we get now a final contrast of about 100,000. Now you can separate it out now. Okay, now we can separate. We can look for a CO signature. We can look for the water signature and methane, and you can see very nicely. Yes, you see the CO, you see the water, and in this case you don't see any methane. Now this is just an example to show you how well this works. At a resolution of 100,000, this can even work better. The problem is that we don't have integral field units yet that actually do with this, but you can use a slit if you know where your planet is. So this is what we did, again, for the same planet, for beta Pictoris B. Note that in real time, this observation was actually before the symphony data. This is a direct image of the GPI instrument. We know exactly where the planet is, and we use the CryRes instrument to put a slit here on the star and the exoplanet. The planet is in this case about 0.3 arc seconds away. It is in an orbit of about 20 years around the planet, around the star, and has a mass of about 11 Jupiter mass. This is what the exo data look like. This is the position on the exo slit, and on every slit position we have a spectrum. And this again, the spectrum is completely dominated by the spectrum of the star, which we know the star spectrum well because everywhere on the slit it is the same, and we can remove that as well as possible. These are the residuals, and then we look for, in this case, carbon monoxide lines within this spectrum. We do that for each place on the slit using cross correlation methods. And this is the actual result then. This is now the position on the slit. This is velocity. And we see at the position of the star we don't see anything. This is the stellar velocity. And we see at the position of the planet we see a clear signal. First of all, it's blue shifted by about 15 kilometers per second. That's because of the orbital motion of the exoplanet, the planet at 8 AU distance, doing about 20 years for its orbit. And what is very nice, we see that this absorption signal is broad. It's about broadened by 25 kilometers per second, and we think that's because of the orbital of the exospin. So the planet is actually rotating around this axis. We know more or less what the radius of this planet is. That means that 25 kilometers per second, that the length of day is about 8 hours. Now that is really fast. But if you plot the planet mass as function of the spin velocity, then you see actually for the planets in our solar system, Mercury and Venus are somewhere below here because of tidal forces. We have Mars, Earth, Uranus, Neptune, Saturn, Jupiter. So we see the more massive the planet, the faster it actually rotates, and also beta Pix seems to fall very nicely on this graph. This is hopefully in the future we can learn a little bit how planets actually acquire spin. We have a few more planets. Before CRIRES was put offline, we had a few more planets measured, and we have, this is really a cartoon, but we have sort of an idea that some of the new planets that we observed were actually very young, and they seem to spin slower, and we think that means that maybe they're so young that they're still bloated, and they're still only after they have contracted they start to actually spin up, and so we see those planets possibly in their very early phase. Now the last two slides, I want to look at into the future of this method, combining the high dispersion method with direct imaging. There's a great instrument planned, one of the 3 first light instruments for the ELT, which is METIS, which will have an integral field spectrograph with a resolution of 100,000, for which you can use this method very well. This is an example of a rocky super-Earth around Alpha Centauri, what kind of observations you could do. And we search here for a planet which has an atmosphere which is exactly the same as the atmosphere of the Earth. So we have to observe an atmosphere which is identical to the atmosphere we are looking through. And the only way to actually differentiate between these two is if there is an actual radial velocity difference. So we see the planet light of the planet around the star at a different velocity than our own observer's velocity. And that's what you see here. This is the position. Here, these two axes are, this is the position on the sky, and this is velocity. This is now the actual star. At the position of the star is very noisy. And you see also this plane here is very noisy. That is 0 velocity. That's, if there would be an overlap between the exospectrum of the planet and on the star. But we see here, this is the position of the planet, the planet that we have put in here. And you see we see it because of the radial velocity offset, in this case of about 30 kilometers per second. Now, it's a nice thing if you would observe it a few months later, it would not only have moved spatially, but also in this velocity plane it will have moved because the radial the component has actually moved. Now, then there is, of course, we will have to wait for METIS. This will be great also to observe the new planet around Proxima, and Christoph Lovis came with a very interesting idea. Could you already use the VLT to actually observe Proxima B? And then we talk about reflected light in the actual optical, and it's going to be very difficult because the planet would only be at about 2 lambda over d at 7,500 angstrom. And we are talking about a contrast of 2 times 10 to the minus 7. But his idea is if you if you couple sphere with the new Espresso, that you could maybe do actually this. Now, it will be very difficult. There will be changes to spheres, changes to actually Espresso, but we're really looking into this now. And the idea is that maybe we could get reflected light of such a planet in about 30 nights. And this is really pushing it. Oxygen, you would need about 60 nights to actually do this. I think in the end, this will be very difficult to actually do. But it's very important to build such an instrument. With this, we learn how to actually build such an instrument, because we really want to build something like this for the ELT, because this high dispersion spectral observations plus direct imaging combination scales with the diameter of the telescope to the 4th power. So with the ELT, yeah, you can do things factor 500 faster or so. So here we're talking about 30 nights. Yeah, for the ELT, this should be easy between quotes. So this is really, yeah, I think this will be the absolute way forward. And I think when the ELT is built and we have such an instrument, so we're talking about 2030 or so, maybe a bit later, we will be able to image Proxima B and measure possible oxygen. With this positive note, I want to stop. Thank you.
So thank you for this very nice overview of what we can do with the current and the future instruments in detecting the atmospheres of these planets. So there must be many questions. Please go ahead. Did you have a question? No, okay. Yes. Wait.
Very quickly, I can. Thanks, Jan Chapas. Just very quickly, with the current instrumentation, what's the best that you can do?
So the best, so the best we can do is what I've shown now. But so the Cryo-S is off the Exo telescope. It will have an upgrade, and the wavelength coverage will be a factor 10 larger. So that means for some molecules like CO and water, yeah, we have really a factor 10 more data in the same time. So we will be able to go a factor 3 deeper. So we really we want to push this to smaller and cooler planets. For the direct imaging part, we really only came up with this method very close to when the instrument came off the Exo telescope. So we definitely have not pushed it yet. For example, the beta pic observations were only like 40 minutes or so. So really short. So there we can, even with the old instrumentation, we could have gained a big fraction.
So Keith has a question, then Stefan, you.
So I was wondering if you are aiming for a detection of O2 as a potential biosignature, but there has been a discussion whether O2 is good enough. So people are thinking about O3, ozone. So the question would be, how long would we have to wait until we be able to detect ozone?
Well, that's a very good question. That's also partly a political question. So we are currently investigating whether METIS should also have an extra arm which goes at 9.8 micron to cover ozone. So we are looking at partners, possible new partners to build such an extra arm, so that we could. For Proxima also observe ozone. The problem is that such observations will be heavily background limited. That means if you start observing, if you then want to observe an object which is factor 2 further away, the object is factor 4 fainter while your noise stays the same, so you have to observe factor 16 longer. So this goes, so if you would need a week of observing time for Proxima B, this already comes out of the question for anything which is further away. So that will be from the ground at least. Ozone would be very limited. Now I'm I'm talking about oxygen because it's kind of, it's a nice, sexy, ultimate science case. There is, of course, a lot of science in between observing CO in a hot Jupiter and doing oxygen on a rocky planet. No, there's orders of magnitude of science in between, and we really need the science for us to understand whether this oxygen is really from plants or whether it has actually another origin.
Why does the required observation time scale with the diameter to the 4th power?
Okay, this has to do with so the diameter squared comes from just the aperture, and then because you're looking at a faint object near a bright star, your basically the noise is background limited from the flux you get from the actual star. Now, if your telescope diameter becomes a factor 2 larger, your angular size of your planet becomes actually a factor 2 smaller. So there comes the other factor 2. Yeah.
When you showed radial velocity measurements of a planet with CO lines, is this measurement based on averaging over all amount of lines, and how many lines did you use actually to get high precision?
We cannot yet see the individual lines within the spectrum. We see them if you squeeze your eyes a little bit, you can see that on the positions where you expect the lines, you see in that on average that there is something there. It's about at 1 sigma or so. But we only see the signal by averaging all the lines. And now the wavelength range that we use so far is quite small. We only have 25 lines or so. So that will be nice after the upgrade. We will have actually hundreds of lines, and therefore this method will actually become a lot better. Yeah, but so that's why you really need the resolution of 100,000 to actually do this. Then you start to see the separate lines.
So next question up here, Derek.
In your visualization of the METIS data cube, you mentioned that the stellar velocity distribution is dominated by noise, right? So did you mean just statistical noise, or is it related to the outliers of the photospheric velocity distribution?
You mean this?
Yeah, because it's much wider than the orbital motion. So.
Yeah, this is really. This is just photo noise. So you have, at this position, you have 100,000 more photons from the star than you've actually here. So this is why this part is so much more noisy. And it's just the way I had to do the actual scaling here, that beyond a certain point, everything is white. It just means high noise. But if you would do this more carefully, then right in the center it would be significantly higher than a little bit away from it. So this is actually, I'm not completely sure, but I think this is stellar noise limited, and this is more, this is already background noise limited. It's not so much from the actual star.
So Roy has a question, but use the microphone, please.
How complete is our census of small planets around nearby M stars? In other words, how many systems like TRAPPIST-1, not necessarily with multiple planets, but one or more, are still to be discovered and then later to be characterized with ELT?
Yeah, it's a good question. So for the TRAPPIST-1, I know that the TRAPPIST team found this planet found the first 2 planets in this system after a few week observation, or maybe a few months, and they just dropped everything and monitored that. So they just stopped looking after they found the TRAPPIST-1 system, and only recently they started looking again for other possible planets. So for the transiting planets around M-dwarfs, we don't know much yet. At least for these very, very low mass planets. There has been the actual MERS survey, which has been going on for much longer. They have also recently discovered an Earth-sized planet, LHS 1140, I believe it's called. But they certainly also still have a long way to actually do. For the radial velocity, it's a little bit the same. So Proxima B is found, and that's actually the first star where they did this very long sequence of observations of 60 nights or so. And they only start to do now similar observations for many, many more stars. So this is the pale red dot team that is doing that. And also there I know that there are already new planets and very nice things are coming out, but I don't know the actual, I don't know the names of the planets. But so no, that's clearly there's going to be a lot more of these. Yeah.
Okay, next question, Tom Herbst.
Yeah, you didn't mention the effects of refraction in the planet's atmosphere. Surely that has some effect. Maybe it just washes out, or?
Yeah, that's this is a problem for the actual transit measurements. Yeah. So if I go back here.
You had a straight line going through.
For example, here. So here we have the say the effective radius of the actual Earth as function of wavelength. And actually, it's impossible to actually probe anything below 10 or 15 kilometers because of the refraction. But we are really sensitive in this method, at least, really sensitive to these very narrow and high lines. So for us, it's not a problem. But if you go, and that's actually very interesting. If you would build a space telescope or so, and you would want to do a similar observation, but then at much lower spectral resolution, actually the strongest absorption comes from this bulk absorption here. If you would integrate this whole absorption feature, actually a large fraction of that is coming from this base here, and that is exactly the part that you cannot probe well in this way. So it is a bit of a challenge. Yeah.
So let me also ask a question. You have focused very much on terrestrial observations. Can you say about additional future space missions that may help here in this context?
Yeah. So of course, first fingers crossed that James Webb will actually work well. I think for transit and eclipse observations, it is difficult to envisage what to do after the James Webb, because this really scales with the number of photons that you actually get or actually collect. So if you think, okay, you can build a larger space not telescope, but yeah, if you go to a 15 meter, okay, you gain a factor of 2. Would that be really worth the effort for doing transit and eclipse measurements? There is another way, that you can go to a smaller telescope and then have a dedicated telescope where you observe many transits, and that is the concept of Ariel, which hopefully gets selected for M4 or 5. So that could be a future observatory to actually do this. For direct imaging, it's a completely different matter. Basically, there has not been yet a dedicated direct imaging mission. WFIRST hopefully will play an actual important role in that to learn how to do this, and then the next step will be to have a large space telescope that can do direct imaging. But then I will be very old, that's for sure. It will be costly.
Let us thank Ignas again for this very nice talk.
Thank you.